In this series of lessons, we'll learn about parametric curves. We'll start with parametric equations, and then we'll go on to calculus with parametric curves, including tangent lines and arc length. Let's start by thinking about what is meant by parametric equations or a parametric curve. A parametric curve, we're going to start in two dimensions, so it's a curve whose x and y coordinates are defined individually by a pair of functions x equals f of t and y equals g of t. So the key idea here is that x and y are both functions of some third variable. Typically we're going to use t to denote time, but any third variable can be used for the parameter. Theta, the Greek letter theta, is often used. Again, any third variable can be used for your parameter. Often in our applications, we're going to use t for time, and then we'll think about xy as being the position of some object at time t, but any third variable can be used as your parameter. Let's start with a couple of examples. So here we're going to sketch the curve defined by the parametric equations x is 1 plus t and y is 5 minus 2t. So I'm going to start just by thinking about what are the xy coordinates for various values of t. So I'll just start by plugging in 0. It's a nice easy one to plug in. So when t is 0, x is 1 and y is 5. So I'll go to my graph and I'll plot over 1 up 1, 2, 3, 4, 5, and I get the point 1, 5 corresponding to the point t is 0. Next I'll go to t is 1, again just an easy value to plug in. When t is 1, x is 1 plus 1 is 2, y is 5 minus 2 is 3. So now I'm going to get the point over 2 up 3, corresponding again to the point t is equal to 1. Now when t is equal to 2, x is 1 plus 2, which is 3, y is 5 minus 4, which is 1. So now we've got the point over 3 up 1, corresponding to t is 2. Now here I didn't specify that t had to be positive. Often in your applications t will be time, so it will need to be positive. If t could be negative here, if t were negative 1, x would be 0 and y would be 5 minus 2, so 7. So we'd be up further on our y-axis, up here at the point 0, 7, corresponding to t is minus 1. So it looks like, my picture isn't perfect of course, but it looks like we're getting a line for this curve. And when I say indicate with an arrow the direction in which the curve is traced as t increases, we see that as t gets bigger, our curve is going down and to the right. Again, it looks like a line, we're not 100% sure, but it looks like we're going in this direction. So as t increases from 0 to 1 to 2, our curve goes down and to the right. Now let's think about how we could have figured out that this was a line without doing this plugging in of points. So remember the equations we were given, we had x is equal to 1 plus t, and we had y is equal to 5 minus 2t. So again, these were just the equations that we were given. So we're going to do this procedure, which is called eliminating the parameter. So I'm going to try to solve for t and find a Cartesian equation. Cartesian just means y is a function of x. So I'll notice that in x is 1 plus t, I can rewrite this as t is x minus 1. I can then plug that into my y equation and get y is equal to 5 minus 2 times x minus 1, or I get y is equal to minus 2x, and then minus 2 minus 1 gives me plus 2, so minus 2x plus 7. So we see that the graph of this curve really is a line with slope minus 2 and y-intercept 7. One important thing to note, so this is our Cartesian or ordinary equation of the curve, Cartesian equation. So one thing that you want to pay attention to is that when we do this eliminating the parameter procedure, eliminating the parameter is just when we find the Cartesian equation, when we do this, we lose the information about what direction the curve is traced. So the parametric form allows us to figure out the direction of the curve. When we eliminate the parameter to get the Cartesian equation, we do have in some sense a simpler equation, but we did lose the information about which direction the curve is traced. Okay, So we've seen one example. Let's do one more quick example of sketching a parametric curve and then eliminating the parameter. So here, my t-bounds, t is going from minus pi over 2 to pi over 2. So let's just start. When t is minus pi over 2, x is 4 cosine of minus pi over 2. So think about our unit circle. Minus pi over 2 is down here at minus 90 degrees or 270 degrees or 3 pi over 2. Cosine is the x-coordinate, so we get 0. Y, sine of minus pi over 2 is minus 1, so y is going to be minus 5. So we start at the point 0, minus 5, corresponding to t is minus pi over 2. Now I'm just going to plug in a point in the middle. I'm going to plug in 0. Again, it's an easy value to plug in. Cosine 0 is now 1, so x will be 4. Sine 0 is 0, so now y is 0. So now we have the point 4, 0, corresponding to t is equal to 0. And finally, I'm going to plug in that last point, that endpoint pi over 2. Cosine of pi over 2 is 0, so x is 0. Sine pi over 2 is 1, so y is 5. So now we've got the point 0, 5, corresponding to t is pi over 2. And again, we see, so I'll just sketch in our curve. So as t increases, we start at minus pi over 2, go to 0, and then up to pi over 2, so we get our direction. Now, you could plug in intermediate points. You could plug in t is pi over 4, you'd get a point in the middle. You could do minus pi over 4, again, get some point in the middle, but we do have the general shape just by plugging in these 3 points that we did. Let's think about eliminating the parameter here. Here it's not going to be as easy to solve for t because I'd get inverse cosines and inverse sines. But let's think about what we know about sine and cosine. So here x was 4 cosine t and y was 5 sine t. Those were the equations we were given. So what I want to use here, I remember that cosine squared plus sine squared, I remember is equal to 1, one of my trig identities. So I notice that if I solve for cosine t in the first equation, I get x over 4 is cosine t, and I get y over 5 is sine t in the second equation. So now I can use my cosine squared plus sine squared equals 1 and get, okay, x over 4 squared plus y over 5 squared. That's cosine squared plus sine squared, which is equal to 1. So we get for our equation x squared over 16 plus y squared over 25 is equal to 1. And we recognize that this is the Cartesian equation of an ellipse, which is what we got when we sketched our graph. So we see we get this curve that goes down to minus 5 up to plus 5 out to 4. So it's not a circle, it's an ellipse. But what is important to notice is that with the Cartesian equation, we just got the full equation x squared over 16 plus y squared over 25 is 1. With the Cartesian equation, the bounds were what told us that we're only getting the right half of the ellipse. And again, the bounds give us the direction that the curve is traced. So the parametric form gives us a little bit more information than what we get when we eliminate the parameter to get the Cartesian equation.